Welcome to Introduction to Composites. Today is the third day of the ongoing week, which is the 9th week of this course. And in the last class, we just started our journey into the area of generalized Hooke's law for anisotropic materials. And what we had done was we had just defined the strain tensor and the stress tensor. Both of these tensors we had shown that they are of second order, and thus they can be represented by 9 elements which can be organized in a 3 by 3 matrix form. So, now what we will do is we will develop relationship for the generalized Hooke's law. For anisotropic materials. So, that is what we are going to develop, and what we will do is we will first see what kind of stress strain relationships exist for isotropic materials. So, for isotropic materials, what is the, let us say, epsilon x, epsilon y, gamma x y. So, epsilon x, so suppose there is a material and I am pulling it and there is also a shear stress. Okay. So, what is the relation for the strain in x direction? It is sigma x by E x minus nu sigma y by E y, and there is no dependence on the shear stress for isotropic materials, because extensional stress cause only extensional strains. So, no term for tau x y in this relation. For strain in the y direction, it is minus sigma x by E x times Poisson's ratio plus sigma y by E y, and the shear strain is tau x y by G. And I know I can also, if I want to use engendering strain, then it is gamma x y, but if I want to use tensor strain, then I have to use the symbol epsilon x y, and the tensor strain is half of the shear strain. So, this is 1 over 2. Okay. And when I use tensors, I always have 2 indices. So, then I have to write epsilon x x, epsilon y y. Okay. So, this is for isotropic material for if it is loaded in 2 dimensions. If it is loaded in 3 dimensions, then I add another term here minus nu times sigma z by E y and so on and so forth. Okay. So, that is the thing. So, essentially what I can, so just for this 2 dimensional stress strain state, I can express this in a matrix form epsilon x x, epsilon y y, epsilon x y is equal to 1 over E x minus nu over E y minus nu over E y E x 1 over E y and 1 over G, like this, and we have, and then because I am using tensor notation, so I have to put 2 indices. So, sigma x x, sigma y y and tau x y. Okay. So, this is a 3 by 3 matrix, because here I am having only 2 stress, I mean only stresses and strains only in 2 directions. But essentially let us call this matrix as A, some matrix as A. So, and let us call this strain vector as epsilon, and let us call this stress vector as tau. Then I can rewrite this whole set of equations as sigma equals inverse of A times epsilon. So, this is the strain tensor, this is the stress tensor, this is the strain tensor, and this is a matrix which connects stress and strain tensors. Okay. And let us call this A inverse as B, then this is equal to B times epsilon. Okay. So, in general I can write it as, now x, if x corresponds to the first direction, then sigma 1 1, sigma 2 2, sigma 1 2, right, is equal to this B matrix times epsilon 1 1, epsilon 2 2, epsilon 1 2, and let us number these. So, B we will, so we can calculate all these elements, we can calculate all these elements from this matrix. I can find what is the value of A from this, and if I take its inverse I know what are the values in B matrix. But anyway I will just use general symbols. So, let us say this is B matrix is B 1 1 1 1, and I will explain this for a moment. So, then it is B 1 1 2 2 and B 1 1 1 2, and then here it is B 2 2 1 1, B 2 2 2 2, B 2 2 1 2, and this is B 1 2 1 1, B 1 2 2 2 and B 1 2 1 2. These are the 9 elements of the B matrix, and we know how to calculate these different values using the process above. And let us just understand this, what all these terminologies mean. The first two indices B 1 1 tell us that they are related to the first equation sigma 1 1. Okay. So, B 1 1, B 1 1 1 1, B 1 1 2 2, B 1 1 1 2, they are being used to compute the value of sigma 1 1 in terms of epsilon 1 1. Okay. And the second two indices relate to the indices for these guys, strains. Okay. So, what that means is that B in general, if we call it alpha, beta, gamma, delta, this is in general 4 terms. The first two terms can tell us, connect this B matrix to the stress, and the second two terms indices connect to the strain tensor. And alpha, beta, gamma, delta, for this they can assume two values 1 and 2. So, in that case they have two sets of values, but for a 3-dimensional system, if the material is not isotropic, alpha can have 3 values, beta can have 3 values, gamma can have 3 values, and delta can have 3 values, right. So, there will be B alpha, beta, gamma, delta can have 81 possible values. For what? For a 3-dimensionally fully loaded anisotropic material. For isotropic material, some of those values will be same. For instance, B1111 and B2222, they may be same, they will be same. But for anisotropic, generally anisotropic material, this B, because it has 4 indices alpha, beta, gamma, delta, and these indices are related to, each index can assume 3 different values. So, it can have 81 possible different values. That is one thing. The second thing is that B is a 4th order tensor. Why is B a 4th order tensor? Because it is a constant which connects stress and strain, and the first 2 indices relate to the stress portion and the second 2 relate to the strain thing, and it connects stress and strain. The stress tensor itself is 2nd order, right. The strain tensor itself is 2nd order. So, if I have to calculate B, if I have to find B, it depends on 4 different independent set of directions. 2 directions are associated with the stress tensor. What are those 2 directions? They are the direction of the force and they are the direction of the plane on which it is acting. And similarly, the strain tensor relates to the length, the direction of the length and the direction of elongation, the direction of length and the direction of elongation. So, 4 different stress directions are associated with this B term. So, that is why it is a 4th order tensor. Another way to look at it is that, for instance, E for isotropic material, E is what? Sigma by strain for a uniaxial loaded specimen. But then epsilon is if it is 2nd order tensor and sigma is a 2nd order tensor, then E becomes a 4th order tensor, because this is associated with 2 directions, this is associated with 2 directions. So, E will depend on 4 independent set of directions, okay. 4th order tensor. So, in general, for anisotropic material, we can say that sigma ij equals E I j k l, E is the 4th order tensor, times epsilon k l, and then I have to add them up. Like here, when I do this matrix operation, what do I do? Sigma 11 equals B 11 11 times epsilon 11 plus B 11 22 times epsilon 22 plus B 11 12 times epsilon 12. So, I am adding on these second 2 indices, right. So, similarly, I will add them on the second 2 indices. So, just to make it clearer, E I j k l epsilon k l, and I am adding on index k, and k can have values from 1 to 3. First axis is x axis, y axis, z axis. So, it can have 3 different values, and L can also have values from 1 to 3. Okay. So, these are 81. So, this is what? How many equations? 9 equations. 9 equations. Why are there 9 equations? Because I can have 9 different values of sigma, sigma 11, sigma 22, sigma 33, sigma 13, sigma 23, sigma 33, and so on and so forth. So, in other words, I can have 9 different equations, sigma 11, sigma 22, sigma 33, sigma 12, sigma 23, sigma 31, sigma 21, sigma 3 2 and so on and so forth. So, we will have 9 different equations, and so essentially I will have a matrix for sigma, a vector for sigma, and there will be 9 rows, and this will be the E vector. E matrix will be a 9 by 9 matrix represented by Eijkl, and this will be again the epsilon vector, which is the strain tensor, vector for strain tensor. So, this is E. So, this is 9 by 1, this is 9 by 1. So, this is the generalized tensor relationship for a fully anisotropic material. Next, we know, so what we do is that we make the writing of this equation a little simpler, and we do that. So, in tensors, in tensor notation, whenever an index is repeated, summing is implied. This is a convention we follow for tensors, not for other situations, but wherever we write tensor equations. So, this is a tensor equation. Okay. So, in tensor equation, whenever an index is repeated, it implies by default summation. So, what do we see? That k is repeated, k is in Ijkl and k is in epsilon kl. Okay. What that means is that we are going to add whether we have this symbol or not, because it is a tensor equation. It is a, on the right side all the entities are tensors, on the left side all the entities are tensors. It is a tensor equation. So, this symbol is not needed because it is implied by default. Okay. If it was not repeated, then we cannot say that some addition is happening, but if k is repeated, then the addition is implied. Similarly, we see that the index L is also repeated. So, we do not need this explicit symbol for addition also. So, for this reason we can simplify, because that makes things simpler and easier to manage, that is all, for management purposes only. So, sigma ij is equal to Eijkl epsilon kl, and these indices are implied, are repeated. So, implies add on indices k and l. Okay. We do not have to explicitly put these symbols for summation. So, in books where they use tensors, you will always find this kind of a notation, and you will not find summation symbol when it comes to tensors, because if an index is implied, it by default implies, if it is repeated, then it by default implies that the thing is added up. So, what we have gotten is the tensor equation for, I will once again write it, Eijkl epsilon kl. This is the tensor equation for a fully anisotropic material. It is the tensor equation for fully anisotropic material, and it involves 81 constants. E I J K L. These constants may be independent or not independent, we will talk about that later, but we are starting with 81 constants. So, what that means is that if we do not know anything else, then if I have to characterize an anisotropic material, I have to find its 81 different elastic constants. That is what it means. If I have an if I have an isotropic material, I have to only find two, one is E and the other one is Poisson's ratio, because the shear modulus, what is it? It is E over 2 times, no, yeah, E over 1 plus 2 nu, right, and so on and so forth. So, I can express the shear modulus and the bulk modulus of a solid isotropic material in terms of E and nu. It has only two elastic constants, independent elastic constants. For anisotropic, it is more than 2, much more than 2, and right now we see that it requires 81 constants. Now, all of these are not independent, but it is certainly more than 2, and we will try to explore how many actually we really need. So, this is there. Next, we know, what do we know? That sigma ij equals sigma ji. Okay. What does that mean? What that means is that if there is a body on which I am applying some shear stress, and let us say this is my direction 1, let us say this is direction 2, then what is this stress? This stress is sigma, the first index is the direction of the plane, direction of the plane is 1, second index is direction of the force, force is in 2 direction. So, this is sigma 1 2. Okay. Now, let us look at this shear stress, it is the direction of the plane is in the 2 direction, right. So, sigma 2, and the second index is the direction of the force, force is acting in 1 direction. So, sigma 2 1. Okay. So, we know that sigma ij equals sigma ji, and why do we know? This is true from Newton's laws of Newton's law of moment equilibrium. So, if you go back to your solid mechanics books, you will see that there is a proof that if we apply Newton's laws of moment equilibrium on this body, if the body is in equilibrium, then sigma 2 1 and sigma 1 2 they have to be equal to each other, they have to be identically equal as long as no point moments exist in body, no point moments exist in body. And in most of the cases this condition is always true. So, if that is true, then sigma 1 2 is always equal to sigma 2 1. Similarly, sigma 1 3 is always equal to sigma 3 1 and sigma 2 3 is always equal to sigma 3 2. So, what that means is that sigma 1 2 equals sigma 2 1, sigma 2 3 equals sigma 3 2, and sigma 1 3 equals sigma 3 1. Okay. So, with this understanding, let us look at, so what does that mean? Okay, so this is there. So, our original equation is sigma I j equals E I j k L epsilon k L, and we are summing on indices k and L. Okay. Now, if sigma 1 2 equals sigma 2 1, sigma 1 3 equals sigma 2 3 and sigma 3 1 equals sigma 1 3, that is sigma I j is equal to sigma j I when j is not equal to I, when j is not equal to I, because sigma 2 2 3 1 is equal to 1 3, 1 2 is equal to, okay. So, this is sigma 3 2, okay. So, what that means is that if these things are true, then at the end of the day how many equations we will have? This will be 6 parameters only, because now we have only 6 different stresses, sigma 1 1, sigma 2 2, sigma 3 3, sigma 1 2, sigma 2 3, sigma 3 1. All the other stresses are just repeated, right. If we calculate sigma 1 2, we have already calculated sigma 2 1 and so on and so forth. So, in this term EIJKL, the total number of independent combinations for, so what that means is EIJKL, now that will be true only if EIJKL is equal to, otherwise EJIKL, right. So, if this is the case, then EIJKL is equal to EJIKL, otherwise these equivalences will not exist, but they have to exist because of Newton's law. So, if they are true because of Newton's law, then this has to be true, because this cannot violate the Newton's law. So, and that if that is the case, then what that means is, so initially indices I and j were collectively responsible for 9 different combinations, right. I was responsible for 3 combinations, j was for 3, so 3 times 3 is 9. Now, these things become 6, right, and this is still 9. So, because of stress symmetry, so the total number of, so because EIJKL is equal to EJIKL, number of constants, it goes down to 54, it goes down to 54. And this is because of stress symmetry, that is sigma ij is equal to sigma ji. Okay. So, this is where we will conclude today. We will continue this discussion on elastic constants for anisotropic materials, and we will continue this discussion and we will see if we can reduce this number even further down. So, that is all for today, and we will meet once again tomorrow. Thank you.